For over a century, cosmologists have believed that the universe began with a single fiery moment, the Big Bang. But what if that story is incomplete, or what if it's even wrong?
This is a billion-dollar question. And what is a singularity? I mean, it's certainly a catchy word. There's an illusion. It gives an illusion that we know what we're talking about.
My guest today, Professor Niayesh Afshordi, is a professor of astrophysics at the Perimeter Institute and the University of Waterloo. He and his colleague Phil Halper argue that the real battle in science is over the mysteries of singularities, those points where our equations collapse and space, time, and physics itself seem to break down.
Where I talked to Niayesh Afshordi and Phil Halper about exactly this question. What happened at or before the Big Bang?
Yeah.
We don't know the answer. We don't even know whether the Big Bang was the beginning.
In their new book, Battle of the Big Bang, they take us inside the fight to understand whether the Big Bang was truly the beginning of it all, or whether it was just one chapter in a far stranger cosmic saga. Let's go.
Soon you'll hear why many cosmologists no longer believe the Big Bang marked the beginning of time, and we'll find out exactly what it does mean to one of the most preeminent cosmologists of our generation. But first, what if I told you the biggest myth in science is the one you were taught as a fact in high school? Welcome to the Into the Impossible podcast. I'm Brian Keating, and I'm joined by my friend and fellow, at least denizen at one point of Brown University, cosmologist, a theoretician, intellectual provocateur, and that's Niayesh Afshordi, co-author of Battle of the Big Bang. His thesis, along with his co-author, Phil Halper, right, is that the origin story of our universe may be a creational myth. A brilliant one, perhaps, but a myth nonetheless. And Niayesh, I don't know if you know it, but you were mentioned by name on Piers Morgan recently. Did you know that?
Yes, I know Sean Carroll was kind enough to mention us. Yeah, and we had talked to him recently, and yeah, I'm looking forward to talking to Piers Morgan in the near future, I hope.
It might happen. I want to start there with what are some of the misconceptions that Piers had. So so to set the stage for people that haven't watched it, Sean Carroll had an epic battle with my friend Eric Weinstein. And, Sean used to be my friend, but he doesn't come on the podcast anymore for some reason. But nevertheless, he's a big character in your new book. And so he was debating with Piers Morgan on this segment that we'll put a clip in of. And Piers kind of called him to task for being arrogant to suggest that he is somehow above Piers because he can speculate on what came before the Big Bang. What did you make of that kind of little spat that Piers had? Were there any misgivings that Piers had, keeping in mind that he might represent the views of many of the audience that's watching and listening now?
Yeah, so it's a pleasure to be here. Thank you very much, Brian, for inviting me. We've been friends for a long time indeed, and but it's great to talk to you in this capacity now and see you again. So yeah, so about the Big Bang, it's such a fascinating story, and I think it's everybody. There isn't anyone who doesn't have a strong opinion about it, which is what makes it very fascinating, and it touches all of us. There's a religious aspect, there is a philosophical aspect, and then of course there's scientific aspects of it. And yeah, everyone wants to know where they came from, right? What is that origin of our origins? And indeed, it's where science and religion meet. In fact, it's when I used to give job talks, and I remember one of the criticisms I have of cosmologists that I try to there was this thing called dark energy figure of merit, but I don't know if you remember that. And we said, okay, so we're going to measure your experiment by how good they're going to measure dark energy. And it's like, science is a great thing. It touches philosophy, it touches religion. There are all these aspects. You cannot really quantify how good the experiment is by one number because it's such a much bigger thing. And indeed, Big Bang is part of that. There is not one number that describes the Big Bang. It's an entire kind of ideology and series of ideology. So where we came from is the question, and we've used science to push it, and we've pushed it as far as we can, at least until this point, and that's taken us to the Big Bang. Big Bang is not a story of how things started. What it really is kind of like when we woke up from a dream, if you want, right? So this is the way I want to talk about it, is that the way that and I really appreciate that everyone expects scientists to tell what happened. So they expect the truth. They expect certainty from us. And I think the main thing I wanted to convey from this book was that science is the exact opposite. It's really the story of uncertainty. And uncertainty is the feature where we do have some certainty. That's exception. We do talk about that a lot, but really uncertainty is what's happening. And Big Bang is very basically the uncertainty and certainty, or some level of certainty and complete uncertainty, they really meet each other. So it's kind of when you wake up from a dream, right? So you don't, I mean, you remember some things, and I mean, what we are remembering is kind of, we have all these observations, the kind of experiments you're working on, and tell us something about what happened, but really it's an incomplete story. There's a kind of figments here and there. And then after you wake up, of course, you can remember things. We can see things in the late universe. We could see things very well. But then as you go to earlier and earlier times, there are kind of things get fuzzier and fuzzier. That doesn't mean that we didn't exist before we wake up from a dream. I mean, we know I wake up from sleep every morning. I don't remember what happened or how I felt during the sleep. I have some memories, and I kind of feel when I wake up. But I mean, there's a point where my memory kind of stops, and that's really the way to think about the Big Bang. And it doesn't mean there was magic. It doesn't mean that there was no before. It just means that we cannot remember. And of course, when we talk about memory now, it's really our collective memory. It's not my memory or your memory, but it's all of us getting together and trying to remember using all the tools that we have. And this collective memory still stops at some point, and that's the point of the Big Bang.
And to say that, as Piers did, that it's arrogance to say that you can know what's needed. You talk about the debates between theologian William, I always forget if it's Craig Lane or Lane Craig. I think it's Lane Craig. I have not spoken to, I've spoken to many, deniers, Big Bang deniers, or, science deniers. And I've talked to religious scientists. I've talked to theologians, rabbis and priests. And, when I was on Piers' show to talk about misinformation and disinformation in the context of, people that really believe things like the flat earth or that the moon landing didn't take place, is kind of denial of the possibility of time before the Big Bang. Is that similar to denying, the roundness of the earth or the Apollo moon landings? Where does that sort of fit in, the Big Bang or the arrogance of physicists and scientists generally speaking, to impede upon where theologians feared to tread just 100 years ago?
Hey everybody, I'm usually the one that asks my guests to judge their books by their covers, but today I'm asking myself to judge my own book by its cover. My newest book, Focus Like a Nobel Prize Winner, is chock full of advice, life tips, and focus and productivity tips from 9 of the world's greatest minds, Nobel laureates ranging from economics to peace to physics, of course. It launches September 9th, which is also my birthday. I hope you'll check it out. And my publisher's gotten Amazon to run a special just for listeners of the Into the Impossible podcast. You can get the Kindle edition for only 99 cents. That's less than a new pocket protector. So go to Amazon and get the Kindle copy today, because this special only lasts for the first week after launch.
I think there's certainly a continuous spectrum, I think. And I mean, arrogance is human. So I mean, I think religious people could be arrogant, scientists can be arrogant. I mean, everyone can be arrogant. This is the feature of our humanity. And it just means that we can be certainly more certain about things than we are entitled to, right? And I think kind of my job as trying to be as honest as I can is to kind of highlight that, so certainty, too much certainty is bad everywhere, right? And both Phil and I have kind of dealt with people from various backgrounds. Obviously, as scientists, we do talk a lot to other scientists. In fact, where I'm sitting right now, next door was Neil Turak's office. He had very strong opinions about various models of the Big Bang. And he had models of his own. So we had our own discussions that do get heated. But of course, people with religious convictions also have very strong opinions. So the important thing to realize is to understand that I mean, people can be more certain about things than they're entitled to. So the story of the Big Bang is one that's based on the laws that we know, and then we kind of keep pushing them, and they kind of fail us at some point. So there is that aspect that basically we could be too certain about things, and it's because we keep telling the same story to ourselves, and the story of kind of universe started starting from some point, the point of infinite density or very high density, and there was no time before that. That's a story. That's a story which could be as believable as any other myth, any other creation myth that we have, basically. But it's really a myth, and the reason that it's a myth is that it's based on principles that we know fail, or either must fail, or we don't have any reason to believe that they don't fail at some point. And in these principles, in the case of the Big Bang, is general relativity and quantum mechanics, and these are things that we've tested very well, but we know that they're not consistent, and they kind of come to head with each other when we approach the Big Bang. So when cosmologists and scientists appear to be certain about something, they are kind of pushing their convictions that, I mean, they're right to be confident about, but not at that point today. Like in this room, they're confident about relativity and confident about quantum mechanics. But if we push them to the conditions of the Big Bang, they're not really entitled to think that they're going to hold. And if you ask them honestly, they're going to confess that they're going to fail. So we cannot really be certain about that, right?
So in the book, you lay out not one or two or three different Big Bangs. I forget how many Big Bang, quote unquote, or origin stories do you have there?
We have 25 of them, and in fact, we have a handy table at the end. If you want, I can show you. We list all of them, right? We have a good table. It goes to 3 pages, which lists all.
And it's very useful to have. Although in some sense it may be confusing to people, because when they hear things like the Big Bang never happened, or at least not the way people think, there's a difference, right, between those 22 different, versions or whatever, those 3 pages of text, and people like the renowned, private citizen Mr. Eric Lerner, operating in Western Pennsylvania somewhere, working on neutronless fusion in his basement, who claims the Big Bang never happened, and that is concomitant or tantamount to saying the universe is not expanding. So what sense do you mean that there's sort of a difference, and I think we could agree that the singularity in the Big Bang is different than saying the hot Big Bang, where we mean the formation of the nuclei, the formation of the CMB, other types of fusion of quarks, fusion of protons with neutrons and higher order elements, and then later fusion of electrons with those protons to make hydrogen, et cetera, et cetera. So what does that mean? Where would someone like a Big Bang denier, who believes the universe itself is not undergoing expansion, and that is a lie, as the Big Bang is a lie according to them, as similar to the round Earth. So where do they fit into this picture? And aren't you potentially worried that this book may give ammunition to people that will say, see, this eminent, brilliant cosmologist working at one of the best and most unique institutions in the world, he says the Big Bang didn't happen, or at least the way we didn't think, right? So where does that fit in?
That's an excellent question. And I think to some extent, cosmologists have themselves to blame, because when we talk about the Big Bang, and I'm sure you had this problem, that we often mean very different things, and we kind of be very confusing. And it's just, but Big Bang, it means this, no, but it means that. And then certainly, I mean, usually in like professional conferences, we know what we're talking about, but then if it kind of comes out, it could be very different things. And in fact, this is a fascinating topic. We did a survey on this very question: that what does Big Bang mean? It was a conference in Copenhagen, and this Niels Bohr Institute of Physics, which is a very renowned center, goes back to the beginning of quantum mechanics. And there was a big conference it was mainly about black holes, but various aspects of astrophysics and cosmology. And we surveyed 85 physicists about what do you think Big Bang means. And there could be different things. In fact, some people say Big Bang means singularity, that there's a point of infinite density and pressure where time kind of starts. There's no time before that. It could be that maybe there is no singularity, but still time starts at some point. Or it could be that, in fact, Big Bang doesn't say anything about the singularity or the beginning of time. It just means that universe was hotter and denser at early times. And yeah, it turns out of these 12, we asked people 12 different questions on 12 different topics. The only one that there was a consensus on that it was this very question, that Big Bang means that universe started from a hot dense phase, basically. And like very few people, like maybe less than 20%, thought that Big Bang meant there was a singularity, or Big Bang theory means that time has started at some point. So indeed, there is this confusion that people may mean different things, but I think the growing consensus is that when we talk about the Big Bang theory, the part of the Big Bang theory which is grounded in experiments and observations is really physics, or part of a physical cosmology as we know it now, is this hot dense phase where universe was much hotter and denser, and as it kind of expanded, it cooled down, it produced hydrogen, helium, lithium, and later on it produced a cosmic microwave background. And all of these we have now tested with very good precision, some of them better than others, but they're all kind of very well founded in experiments. And that's the part of Big Bang theory that I think there's a growing consensus that is the Big Bang. And then what came before that, whether there was inflation, whether there was a singularity, maybe universe kind of bounced out of something, maybe time did start out of at some point. All of those are kind of pre-Big Bang models. So that's not really the Big Bang. That's what came before. And yeah, there are many possibilities. We don't say that nothing was there before. It's the possibility that universe came out of nothing. Stephen Hawking had this famously no boundary proposal, but he thought universe actually came out of nothing. But there could be others, and there could have been a universe that existed long before.
Yeah, we'll talk about that. I had on Thomas Hertog recently. It was Hawking's last colleague, and some say one of his best ones since Hartle. And we got into that, and I do want to ask you about that as well. But before we get there, because I think Hawking just has this outsized influence on cosmology. I only met him once. And he only said one thing to me, which is that, the reason his book was written, the Brief History of Time, was to pay for his daughter to go to college, but which made sense because it was very hard to understand until I was much, much older. But one thing he worked on is to avoid, boundaries and singularities, and that you make the case in the book that effectively the belief in the singularity, or at least the singularity, is not as taken seriously as it perhaps once was, or perhaps it is by most lay people thinking about it like a Big Bang as a singularity. So first of all, is a singularity something that's real? Because I think a lot of people see it as, I think Hawking said where God divides by zero, but then people like Kruskal and Kerr and Penrose can do all sorts of mathematical tricks, as they call them. And Hawking called the Wick rotation a trick as well. And then he goes on to use it to make points about how the no boundary theory is right. So first of all, before we get there, what is a singularity? Is it physically real in the sense that it can be detectable, even in principle, if we can't detect it, right now?
Very good question. And I think this is a billion-dollar question. And what is a singularity? I mean, it's certainly a catchy word, one that, we throw around all the time. We say there's singularity inside black holes, singularity at the Big Bang. We can use it easily, but it is there's an illusion. It gives an illusion that we know what we're talking about. And this is really the thing, right? That if we say this so confidently. I've been teaching astronomy in my university, University of Waterloo, for the past 13 years, and I use a textbook. It says heart of black holes, there lies a singularity. This is why we all say that confidently. And I cannot, hold my face straight when I say that. I shouldn't, but anyways, this is an undergraduate course, and usually, the students don't necessarily, this is for engineering students who don't necessarily care about all the nuances of this. But I should be, I'm very respectful of engineers, so I'm not. Here's the thing: is that the singularity is exact opposite of what we know we're talking about. We say something, but we don't really know what we're talking about when we say singularity. This is important to know that there are some places in science that we basically just fail. And of course, it's not as nice and as confident as, oh, we just failed. We don't say that, so people think, okay, that's an embarrassing thing to say. So we said, no, there's a singularity there. But they are basically the same thing. Saying a singularity is just saying that we failed, we have no idea what's going on. So that's what it is, and basically what it is you take our models, our theories, and we push them to their logical extremes, and then we see that there is a point at which they fail, right? So they just cannot make a prediction anymore. So what we can be confident of is that our theories fail. So we cannot really use these theories anymore. Now, the question is, okay, is this something you can be proud of or not? I suppose that's a personal decision. But it is basically at some level, there is some certainty that we cannot use our theories as we understand them right now anymore. So that's some sort of a certainty probably. But on the other hand, it's also a confession to failure, because we just don't know what's going on. We need better theories. And it's a call to arms, that it just means that we have to find these better theories. And that's a singularity. Singularity is just you take the laws, you push them, and at some point, it cannot be pushed anymore. And that means that we need better laws, and that those are yet to be found. We have been looking for better laws, basically a theory of quantum gravity. Maybe it's a string theory, maybe it's loop quantum gravity, maybe something else. But singularity just means that this is a place where we need something better, and
Do we really need it though, Niayesh? Because if I'm not mistaken, there's only two instantiations of singularities known to physicists in general, or at least in cosmology, and that's, at the origin of the universe, possibly, although half of the models you talk about don't have such a feature, and then at the center of a black hole, where we seem to have violent disagreement and conjecture that's just as wild, but the one thing that we know for sure is that we can't access either one of these, at least using causal relationships. So does it matter? Does it even matter that singularities aren't convincingly demonstrable? And perhaps are we wasting tons of talent and money? And obviously the people are the most important thing not to waste, going down these rabbit holes where we can't find anything inside a black hole to begin with. Is it just a fool's errand, perhaps? And especially when it has very low ROI, right? Because it only might apply to two objects in history, the Big Bang and a black hole. So why waste all that? There's 100 billion other stars in our galaxy alone. Why waste our time on these two different places? I'm kind of being a little bit provocative here, but I think you understand.
Yes, of course. No, this is an excellent question, and then indeed, I think it has to do with. I think there is a logical question, and there is a kind of sociological question there. So the logical question is, so we have a disease and we have a symptom of the disease, right?
Yeah.
And singularity is a symptom, right? The disease is that we have these two theories that don't work together, quantum mechanics and general relativity. And the symptom is the singularity. But when you detect the symptom, does it mean that, okay, if we just ignore the symptom, will the disease go away? And it just, it's like, I take aspirin, I take Tylenol when I have a fever, so okay, I don't have a fever anymore. But the disease is still there, so you just kind of mask the symptom, right? So, and that's the important thing. And there are in fact more explicit examples of this. Like, for example, in fact, this year is the 50th anniversary of the black hole information paradox, which was basically this discovery that Hawking did around 50 years ago, that black holes, in fact, are not black. That if you add quantum mechanics, they radiate, and in fact, at some point, they could disappear. So the mystery there is that, okay, what happens to all the information that goes into the black hole? Now, the black holes are big. Black hole at the center of our galaxy is big. It's much bigger than the Planck length. It's not going to evaporate anytime soon, but nonetheless, you could imagine that a black hole that's like set out there in the vacuum, it's going to evaporate at some point. And there's this question of, okay, so how could the information get out? And it turns out that you actually reach paradoxes, even the black hole is very big. But within, you have to wait a while, but black hole doesn't have to get very small for these paradoxes to come about. And in fact, we are organizing a conference at the Simons Institute, Simons Center in Stony Brook in the fall to kind of discuss various ideas for how the information can get out. I mean, there are many ideas, but this puzzle has been with us for the past 50 years. And this is basically somewhere, it's not at the singularity, it's yet another symptom of the disease. And this is the problem. If you do have a disease, which is this inconsistency of these two fundamental tenets of physics, the symptoms are going to show up here and there. And you could just kind of say, okay, maybe this doesn't affect me right now, but it means that disease is there. So the symptoms are going to show up elsewhere. And some of the problems we have in cosmology may be due to this. So we have all these issues that maybe the rate of expansion of the universe we measure right now seem to be inconsistent from supernova observations and from cosmic microwave background. Maybe that's another symptom. We don't know. Maybe it's just purely experimental. But this is the thing, that if until we actually address the disease itself, we don't really know these things that are happening here and there. Are they really related to this disease, or are just symptoms I can just ignore? So this is really the answer to that.
One thing that's so fascinating about you is that you're not provocative for its own sake, the way maybe I've been accused of being, but you're also not scared to bring up hot button issues. And I think your perspective as an Iranian American, or I don't know, are you a citizen? Oh, now you're in Canada, but you came to America right before 9/11, which wasn't a great auspicious time for a Muslim man to come to the United States, perhaps. And I imagine that was traumatic for you, but obviously it was very traumatic for a great many other people in a much more serious way. But how did your upbringing? I've always been curious about you. Are you still practicing? I mean, if you don't mind, if you feel comfortable talking about, I'm a practicing Jew. I'm not like Orthodox, but I do, keep the Sabbath, for example, because I believe that there are actual benefits to, my mental health from refraining from work and technology one day a week. And I often, encourage my students, one of whom is a brilliant Iranian American as well, by the way. You should be proud of me. And I just want to kind of get a perspective. Does religion play a role in your life? Because obviously it's the first sentence of the Torah, right, is concerned with something about some kind of beginning. I mean, that's what it means in Hebrew. It means in the beginning of, and it's our motto in the University of California. Even let there be light. What Hashem or God or Allah or whatever you want to say did. So, does religion have any place in a working cosmologist's arsenal, so to speak?
That's the fascinating question, and then it's such a fascinating question. We have a whole chapter in our book dedicated to this, because in fact, I don't remember everyone has told me, like, I think my wife in particular told me that don't talk about religion. It's people don't take you seriously if you talk about religion, and it's.
That's the opposite of what Stephen Hawking's wife said.
Is that right?
He put the mind of God in there because he didn't believe in God, but he knew it would sell more book copies. And his wife was very adamant that he not be too militantly atheist. So good thing you didn't listen to Ghazal and that he didn't listen to Jane, I think.
Well, I think at the level that the Stephen was, maybe I think there is a phase transition that it could be better. But I think we're probably past that point now. Yeah. I think this is fascinating. I think it touches so many aspects of our life, and I think maybe the baseline is that we are all humans, right? And we all start with our own upbringing, and part of it is personal, part of it is social. And religions are part of our social structures, right? So believe in it or not, it's there, okay? Even if you want to deny, you want to be an atheist, say, I don't believe in any religion, you still believe in something, and you get it from somewhere. And that's been affected by your background. So, in fact, this is one of the questions I like to say, one of the favorite things I say in the book is you can take a cosmologist out of the religion, but can you take religion out of the cosmology?
That's right, yeah.
And that's the thing. So for example, you go to these conferences, as I told you, Neil Turok was next door here. In fact, before this was Neil Turok's office, Stephen Hawking used to visit us before he passed away. And he used to sit next door. I also had brief conversations with him like you. I think he told me I once told him about my theory, and he said the only thing he could say, it took like 20 minutes to say, but he said that it's too ugly to be true. So that was so that was his reaction.
But you know what Penrose said about Stephen and making bets with him, that he was the safest person to make a bet with, because no matter what side you chose, he would always change his mind, so he'd always win.
Okay, that's good. I think, that's that. I think I didn't get a chance to make a bet with him, but that would have been the next step. Unfortunately, I missed that. But here's the thing: is that even the scientists who claim that they don't believe in God and they have the priorities, they have some set of beliefs, and it turns out that if you then have two different scientists, they may have a very different set of beliefs. Neither of them are necessarily very much justified, but they think that this is how nature should work. This is natural. This is not natural, even though we don't really know how nature works. But there are all these discussions that, okay, is the standard model natural? Even the standard model of particle physics, or is cosmological constant natural, or is the universe fine-tuned? And then there are very strong beliefs on both sides. And if you didn't know any better, you would think that these are religious kind of dogmatic beliefs, even though they don't talk about religions. But they have very strong beliefs about, is it string theory or is it loop quantum gravity? And these are all things that are really unfounded in experiments. But nonetheless, there are people who dedicate their careers to them, and then they kind of dismiss or diss anybody who don't agree with them. So that's the thing, that I think religion is with us, want it or not, and I think it's part of our societies and part of our communities. And even if we don't call it Islam or Christianity or Buddhism, it's still one kind of tool, if you want, a hidden tool for us to build communities. And personally, I think I've had an interesting journey with the religion, as I think I detailed in the book. And you mentioned that I grew up in Iran. Iran was a theocratic society. It still is, although probably people argue much less than it used to be, given the government. But it's also very hard to know what's happening in Iran, because it's hard to kind of do a kind of neutral poll or a scientific poll, because everybody's afraid to actually say what they really believe. So it's a tough one. So I grew up in that environment. So we saw the bad things that came out of religion, but also we see, the good things at some level, like was part of our community. And I think that thing has stayed in me, and I cannot deny it. I think I do appreciate the good things that come out of religion, kind of reassurance, solace, tranquility. On the other hand, I also appreciate the ways that religion has been abused to start wars and oppression. And I think we have to kind of appreciate that, understand that, and kind of try to live with that in a way that doesn't destroy our lives.
Does Islam have a perspective on not the Big Bang, but questioning the Big Bang? For example, in the Talmud, which is the second holiest book in Judaism, which is the compendium of 2,700 pages of interpretation, like what does it mean to say an eye for an eye? Like most people have this conception that it means you take out somebody's eye, but that would obviously lead to their death. and the law explicitly says it's measure for measure, meaning you don't kill somebody for hurting your eye or blinding you, even as egregious as that is. So where do we get that, and where do we get that, it's okay to kill a murderer when the third commandment or the sixth commandment is, thou shalt not kill, but it really doesn't say that. It says thou shalt not murder. And so the Talmud is used then to give applicability in a real world scenario. Just like if you took the Constitution of the United States, you couldn't understand, like, am I allowed to chew gum and spit it on the sidewalk? Like, do I get, put in jail for that? So we have a whole set of case laws and so forth. But the reason I bring this up is that in the Talmud, it says that you're allowed to do scientific speculation about what things were like up until the day that days began. It literally says that. But you cannot do so beforehand. It doesn't say what the punishment is, and it's not clear, the famous stories, if you have two rabbis, you have three different opinions. But in Islam, is it permissible to speculate what happened before the Big Bang, so to speak, or the creation of the world?
Well, I mean, of course, it depends on who you talk to, and there are kind of various strains of Islam. And I mean, I'm not a Muslim scholar. I mean, I did grow up in Iran where it was Islamic, and then we did talk about everything. Of course, I mean, the main thing is that you shouldn't question God. And then I guess you shouldn't question Quran, but exactly, yeah. I mean, those are the two things that are really sacred. But about everything else, like, there could be different interpretation of Quranic verses. Some are more literal, some are more kind of try to match it with current scientific beliefs. So there is, I mean, there is a movement, which I think is probably similar to one in Christianity, that they kind of try to interpret everything in the light of modern science, that maybe this is certain things. I mean, there are similar things to the Genesis story. There is a similar version of that. And I mean, of course, you could interpret it in whatever way you want. No, I mean, I think it's, again, it does vary depending on which version of Islam you have. But I mean, it turns out, yeah, Islam hasn't been that, at least in the last few centuries, it hasn't been more about kind of these, it was more about governance as opposed to, I mean, the part that they're strict is more about the governance and power structure, as opposed to, okay, what happened at the Big Bang or not. Yeah, as long as you don't question the authority of the clerics, then then all is fine.
Oh, it's fine. Okay. Well, I want to get to those clerics because you make the point that there are clerics in modern cosmology just the same. And past guests have made similar, very close to Sabina Hassenfelder and Eric Weinstein and others, and even Lee Smolin and certainly Neil and Latham, all these great minds. Anna Aegis was on the podcast many times, or at least once, and Paul Steinhardt as well many times. So there are apostates. There are people who break the orthodoxy. And the one I'm thinking of most is perhaps the one that butters the bread around the Keating household, or the challah. It's Friday, so we're getting ready for Shabbat. So we have challah. We put bread on the table here by potentially detecting the primordial waves of gravity lurking within the cosmic microwave background's beam-mode polarization. And this was the impetus for why Jim Simons agreed with my proposal to start the Simons Observatory back in 2016, and he should rest in peace. He's been gone over a year. But there are many people who don't believe that, especially one of the original members of our external advisory committee. You may not know this, but on BICEP, it was just, Kovac and Clem Pryke and Jamie Bach and Chao-Lin Kuo. And basically they were this, quadrumvirate, and they just decided what to do. And that was different than the way things were before Andrew Lang took his life in 2010. But be that as it may, they just went to the press and went to, Alan Guth and Andre Linde, and the whole story you mentioned in the book. And we'll get into that later on, because I'm not only a character, I'm not only an endorser of the book, on the back, a blurber giving my highest encomium, but I'm also a tiny character in the book, which is nice. But that was kind of made by fiat, literally, by those four gentlemen. And they're all outstanding scientists, but suffice it to say, if we had in place what we have now at the Simons Observatory, the so-called External Advisory Committee, where we have some of the most monumental scientists, that are alive. George Stadiou is one of the members. Just for example, Mark Kamiankowski is coming on, Lloyd Knox, John Rule. We have experimentalists, theorists, engineers. And that is meant to guard against the irrational exuberance that plagued the inflationary 1990s that you talk about also in the book from Alan Greenspan. But Niayesh, tell me, are we also creating a cadre, a cohort of individuals who are guilty of apostasy? That there was a letter published by 31 people, including our friend David Kaiser and Andre Linde, signed by those people and Nobel laureates as well, saying that the kind of speculation that Anna and Avi Loeb and Paul were engaging in was not part of the scientific method, and it wasn't a good thing. It kind of reminded me of the Catholic Church in the 1500s, putting down, some responsa back and forth. So tell me, what is your take on this? Are they cleric? Or do we have clerics in modern cosmology that are every bit as powerful, at least to our careers, and not to our lives, thank goodness, but as mullahs or clerics? What do you make of it?
I think the short answer is yes. The short answer is we are humans, as I was saying before, and we live in communities, and communities have ways of setting structures. There are some explicit ways, there are laws, right, you have to follow, but there are also implicit ways, that there are these power structures, right, that people look up to others. And it's not something that's written, but it's not something that's designed. It's something that kind of our communities has evolved. This is how we built communities over the years, through around these power structures. And in the olden days they were called prophets, and now we have, I don't know, mind leaders or visionaries. There are different names for them. They have people. Full professors. I wish. Yeah, I think. Yeah, full professor is not that. It's cheap. I think there are lots of full professor. I'm a full professor. I think it takes more than a full professor. I think I must have a better name for it. But it's really prophets, just modern prophets. But there are many examples of them out there, and basically they kind of set the trends, and then basically they decide that this is an exciting topic to work on. And you would think that, okay, it's not life and death sentences if you disagree with them, but really, I mean, what do we do in our life? So we teach, and then we write papers. But then to write papers, we need to hire students and postdocs. If we cannot get grants to do that, then I suppose we can keep teaching, but then we won't be able to do research. And this is kind of, as a scientist, our life does depend on these fundings, and that's the way things are set up. And if you cannot get funding because for whatever reason, there's this structure is set that certain topics are hot, and if you don't work on those certain topics or certain theories, then what you do is not well motivated. They may call it flat earthers. I mean, if I work on maybe something that's off topic or maybe not mainstream Big Bang model, let's say, they may compare me to a flat earther. I mean, I don't know if it's the fair comparison. I don't know if they're gonna say that, but I think it's the same kind of thinking, that you say the same way that you look at the crackpot, they may look at me, and that would then you're not gonna fund. Give I don't know $100,000 or $1 million to your crackpot. And then of course that would end your. I mean, if you cannot get funding, then you cannot do research, and that's the issue. So I think that's there. The important thing is we have to understand that, I mean, there's one difference, and the difference is that we do have observations. I don't think we can get rid of the social structures, because we are humans and we interact with each other. But if we can actually relate, kind of justify what we do based on observations, then that's one thing that we have on top of maybe one step better than, we are one step ahead of our ancestors who either didn't care about observations or didn't have as much of a technology, basically, to understand the universe and observe the universe. I think that's so I think we shouldn't be arrogant. We should understand that we are all the same, but then we have to kind of understand that, and then in spite of that, try to do the best that we can.
So, Niayesh, one person that plays a big role in this book, in addition to Phil, obviously, is Carlo Rovelli. And Carlo got kind of mad at me last year. I made a video kind of bemoaning the fact and being quite depressed at the fact that perhaps there were these findings that that were contravening and contradicting some of the basic predictions of loop quantum gravity. And this had to do with Lorentz invariance violation and violation of the speed of light versus frequency. And Carlo really just laid into me and said this is misinformation. He basically was calling me, like a cosmological version of Donald Trump, and it was a little bit painful to me. But we kind of resolved back and forth through this, quoting from people. This was based on an experimental result from China that seemed to suggest that certain low energy limits of loop quantum gravity could be ruled out. And so I was basically made a video that popularized a paper that maybe 10 people read, but I was seen by 100,000 people. So I don't think he liked that. But let's talk about that, because one of my problems with him was that, and then Phil made videos, attacking me as well. But that was also to say that that Carlo's the last and final word, whereas I could find in the literature many examples where Lee Smolin said very similar things about that I was saying had been tested and disproven. And again, my point was to say this is bad, because if we only have string theory, which is the 100 million pound mammoth in the room, it's a bad situation. So I thought that would go over well, but obviously it didn't. But it's also equally bad when Carlo's the only person who is responsible for this, kind of promotion of the theory. And then if he says it's not true that loop quantum gravity, quote unquote, predicts this effect, then that's the ground truth. And I think that's what Phil was keying off of. So what is this? Does loop quantum gravity have an Ed Witten problem or a Natty Seiberg problem, which, as you know, Natty once said, when asked, well, what if this isn't, consistent with string theory? Then he said, well, we'll just make it part of string theory, which kind of rubbed people the wrong way. Is loop quantum gravity verifiable? Are there things that we can see if it's true that we can't see polarization delays versus energy? We can't see time delays due to speed of light varying. I mean, what does it predict? How can it be falsified? And in that sense, how is it any better than string theory or worse than string theory?
So I have to be diplomatic here. Of course, Phil is my co-author. Carlo is a good friend. I could see that he says it's an intellectual feast. This is from Carlo Rovelli. So he said good things about our book. But at the end of the day, I guess I'm a scientist, so I have to speak out my mind. And yeah, I mean, I don't belong to any of these camps. I try to be agnostic, and I think all approaches to quantum gravity they suffer from the same problem, that they're kind of cool ideas, but they don't really make concrete predictions, and they're kind of malleable. They kind of inspire things, and the prediction, or I guess it wasn't really a prediction, the idea that at high energies light can propagate with different speeds, that wasn't really a prediction of loop quantum gravity. It's something that was inspired by it. And the statement that Carlo is making that this doesn't happen is also not a prediction of loop quantum gravity. It's inspired. It's just doing doing calculations on larger scales is just, they don't have the right machinery to do it. And it's not that surprising. Even if you ask about what is the structure of a proton, and we don't really have a good theory for it, because you have to use lattice QCD, and you could maybe do it on 10 lattice points. But yeah, so this is a hard theory to do calculations in. And of course, a structure of proton, I think we know the ingredients, but still it's a hard calculation. For loop quantum gravity, even the ingredients not everybody agrees on. Same is true in a string theory. Same is true in causal sets, which is another approach. Same is true in Hojava-Lifshitz gravity, which is yet another approach. And we could go over many of these. And I think it's important to realize that there are many ideas out there, but at some level, they all are just ideas. They're not really theories. We shouldn't really call string theory a theory. We shouldn't call loop quantum gravity a theory. These are all ideas, and they have some structures. Some of them are very mathematically beautiful. Certainly to the people who work on them are very mathematically beautiful, but that's not the reason that they're true, and that's not the reason that they're physics. In fact, they're not. And I think they're all at the same, I consider them, they're at the same, they fail at the same level. It doesn't mean that they're bad, it just means that they have homework to do. And until they do their homework, or unless they can do their homework, they're not really a theory, we cannot take them too seriously.
And is holography in that same camp? I mean, anything that sort of relies on anti-de Sitter space for a de Sitter space, not even de Sitter space. I mean, we don't live in de Sitter space either, but we certainly don't live in anti-de Sitter space. And it seems like a lot of the holographic principle, both for black holes but to a more troubling extent perhaps to the early universe, relies on ADS CFT. So where does that stand? I mean, is that ever, I mean, we don't, the bottom line is we don't have any evidence for extra dimensions. It's always kind of literally swept under the rug or swept under the string. The so-called string bikini or whatever you want to call it covers up a little bit, but by the fact that these are compact and so forth. But the bottom line is we don't see any of these phenomena. And so, I'm an experimentalist. I don't know if you heard, but just yesterday, CMB Stage-4 was effectively canceled. I don't know if you heard.
I'm sorry to hear that.
Yeah, it's a really big blow.
That's not a good thing, right?
It's not a good thing. No, it's not a good thing. But it just highlights the fact we have very limited budgets to do tests, so we have to be discerning, and we have no new accelerator. So, what would you advise, a young experimentalist to make of these really fanciful and wild ideas that you and all my friends that have come on that are theorists? I've had 10 times more theorists than experimentalists on this podcast. Mark Kaminkowski used to call me a deeply closeted, theoretical physicist, that I was, hiding my shame, but I really wanted to be one of you, which maybe is true. But tell me, Niayesh, if you were advising my brilliant student, Shahed, or any of my students that work on experiments with me, what would you tell them to do? Well, how should they waste their, not waste their valuable time?
I think actually you shouldn't call me a theorist. I don't know if you did call me a theorist, but I mean, I guess it's fine. But I mean, really, we come from the same background.
I called you a brilliant theorist, actually.
Okay, so that's even worse. I think maybe that you're insulting all the other theorists then in that sense. So,
no, come on, don't be modest, guys. You, I have to say, you start off at Brown, and you were so good that you were able to, not only work with and maintain an excellent relationship with our really good friend and past guest Robert Brandenberger, but that you were going to work for the president of the Simons Foundation and co-founder of the Simons Observatory, David Spergel. I mean, don't sell yourself short. You can have a little bragging. Your wife's not listening, your in-laws aren't listening. Come on, let's do it.
No, I'm not saying that being a theorist. I'm a bad theorist. All I'm saying is that I don't think I consider myself a theorist per se, because. And I think maybe it's a culture thing. We come from the same background in the sense that we have kind of astrophysics. We're looking at observations and trying to make sense of it. So we both work on CMB. So you were a little bit more on the experiment side. I was more a little on data analysis side. But really, I think there is something that clicked on my mind. And that was when I came here to Perimeter Institute. Because back then, I thought that, okay, so there are these guys who kind of are very brilliant, and then they came up with ideas, and then we should go and test them. And when I came here, I kind of started talking to these guys and realized, okay, these brilliant guys don't really know what they're talking about. So maybe we should decide what we want to look for ourselves. We cannot just be at the mercy of these brilliant guys who tell us what to go and look for.
That's right.
And I think that's the thing, is that... and that's why you may call me a theorist, but really, I started as an astronomer, an observer, I mean, almost an experimentalist, really. And I think I still am to some extent. But I think that at some point you realize, and I don't think that happens for everyone, but I think if you talk to enough theorists, at some point you would realize that they don't necessarily know what they're talking about. So you shouldn't just kind of wait for them to tell you what to do, and then you just kind of try to look for things that make sense to you, and that's kind of where I ended up, how I ended up where I am, which is a kind of trying to, instead of kind of listening to what a string theory says or what loop quantum gravity says or some other idea, just say, okay, so given the observations that we have and the problems that we have, what is the next thing I can look at that could help make progress? So you want science to be data-driven, but also you want to kind of make progress in addressing fundamental problems. And I think that would be my answer, and that's kind of what the way I try to kind of drive my scientific program and research. It's not necessarily very popular because I don't necessarily belong to any of these big camps.
Right, but I mean, your institute's not called the Perimeter Institute for observational or experimental physics. It's this theoretical physics. It's okay. I mean, I think the best physicist, quote unquote, is an experimentalist. And I don't mean that egotistically. I just mean that in order for me to do what I do, I have to understand what you do. I don't have to do what you do. And that's a big distinction. I don't have to come up with new theory. But I teach my students, and I'm curious what you teach your students, but I teach my students that the experimental minimum, to use Lenny's phrase, is that they must know, understand, and be able to be comfortable with theory at the level of a beginning graduate student. But just as a beginning graduate student doesn't construct new, maybe yours do, but they're not making new theories up. I'm curious, what do you consider the experimental minimum? In other words, what is the minimum amount a good student of yours should know about what I do, experimental physics and science in general?
Yeah, it's a good question. I don't believe in absolutes. So I guess my advice to my students is to basically have conversations. And so basically the way I think about science is like language, that it's not kind of, if we want to speak English or Farsi or whatever language you like, it's not that there's a minimum number of words you have to learn or there's a minimum number of hours. And there probably is something like that, but that's not the way we learn language. The way we learn language is by talking. And I think my advice is just, you have to talk to theorists, and then the more you talk to them, the more you understand what they do. Again, you're not going to understand everything they do, but the more you talk to them, the more you understand kind of their mentality, where they're going, what are the big problems they're thinking about. And the same with experimentalists. So I think the key, at least my advice to my students or anyone who's interested in doing science, is that you have to talk to to the scientists, the people who practice it. And by talking to them, you kind of understand their point of view to the extent that you need it. And if you talk to different people, you kind of see where different people come from, and then you can then kind of decide your own path. And I mean, that's what I've been doing. I think one of the great things about being here at Perimeter Institute, and I should say I'm half of my time at Perimeter Institute, the other half is at University of Waterloo.
Right.
There are more astronomers, so I do talk to people who work on galaxy clusters, larger scale structures, planets even. And then here I do talk about people who work on quantum gravity, quantum information, particle physics. And I think by talking to different people, you kind of get different perspectives about what is it that they care about, and then what is it that maybe they should care about. Here's the thing: is that more often than not, these people don't talk to each other. And I mean, for me and the people I talk to, I try to be a bridge at some level, but also someone who can get the big picture. And I think this big picture is very important because there are always lots of details and you can never master all the details.
Right.
But the big picture is what helps you to decide kind of what is the direction that's maybe the right direction for you, or where things should go in the future.
Right. I wonder if we could go a little bit more technically in depth as we kind of wrap up the hour. And that's to talk about this theorem, which kind of bridges the gap between the layperson and the Nobel level, audience member, and that has to do with the Bourdet-Guth-Vilenkin theory. So, can you express explain what that was meant to do, how it may be being misused by theologians like William Lane Craig, and Stephen Meyer, who's been a guest on the podcast as well. So how is it to be understood, and how is it not to be understood?
Right. So this theorem, is kind of what came after the original singularity theorems by Stephen Hawking and Roger Penrose. However, in their theorem, so basically the theorem was that if you have, there are a bunch of assumptions, but mainly the main assumptions for this discussion is that you have theory of general relativity, and then you have attractive gravity, which is kind of the key assumption there. Gravity is always attractive. with these two assumptions, then the beginning of the universe must be a singularity. So that means that the point where density pressure probably goes into infinity, and then time cannot go anymore. So the clocks are stopped at that point. Now, if it turns out that in an inflationary universe, which is the kind of universe which exists right now, basically based on observations, the universe expansion is speeding up. So in fact, gravity is repulsive now. Today on very large scales, not in this room necessarily, but on cosmological scales, gravity is repulsive. But also if inflation was, there's an early universe inflation, which can solve a lot of problems. In fact, that's the most popular theory of the pre-Big Bang, what happened before this hot Big Bang phase, is an inflation where universe, you had a repulsive gravity, but at much, much higher magnitude. So universe expanded kind of by many, many orders of magnitude in a tiny fraction of a second. So they kind of extended that theorem, singularity theorem, to that situation with repulsive gravity, and they showed that indeed there is also a point where the clocks are stopped ticking, at least if you have an expanding inflationary universe. So yeah, so that was the idea, but it's actually there are kind of simple loopholes in it, in a sense that if your universe was kind of contracting, then there was no problem. So they just said maybe it's possible the universe just goes from contraction to expansion. There's nothing singular or weird that's happening here. It's just kind of a turnaround. So that's one kind of exception to that. But also it's a classical theorem. It's based on ignoring that the fact that the universe is in fact there's quantum mechanics in the universe. It's just based on classical general relativity. I mean, these are two main loopholes, and but then the thing is that people have kind of pushed this and said that, especially people with religious convictions like William Lane Craig or Steve Myers, as you mentioned, that okay, so you can use this to prove that there was a beginning of time, and that must have been, maybe there must be an intelligent design or creator that has started everything. And I mean, I think just the same. My answer to that is the same as like the question about the singularities. That this singularity or point where the clock stops ticking doesn't mean that the science ends. It just means that we need something more. And it could be, in this case of BGV theorem, as simple as just universe was not expanding, it was contracting. Or it could be that we have a quantum theory. And then that's it. It's just that we need a little bit more to push things beyond that point. And that's my response to that. Mm-hmm.
Okay, so the other topic that I want you to discuss are the four things in the singularity theorems of Penrose and Hawking that people assume, and why do you reject all four? And if so, what could replace them?
Right. So let's talk about the four of them. So I think I mentioned two of them, which was you have attractive gravity. So that's where the singularity theorems are kind of the strongest. And then the other one I mentioned was theory of general relativity, classical theory of general relativity, what Einstein developed back in early 1900s. The two other assumptions is that you have 3 dimensions of space and 1 dimension of time, which is kind of what you expect in general relativity, but there could be weird exceptions to that. Like for example, Hawking at some point decided that in this no boundary proposal, maybe there's just 4 dimensions of space and no dimension of time. So that's the way that he could avoid the singularity theorem. But it's kind of just a shorthand for just thinking that really classical general relativity fails, and there's some sort of quantum theory that should happen. And the fourth assumption is that there are no time machines, which is something maybe you take for granted. Although if you watch any movie, like every second science fiction movie has a time machine in it. So
right, exactly.
So you would think people would take it more seriously, but in fact, my good old professor Richard Gott, in fact I TA'd for his general relativity course. But his favorite topic is time machines, and he thought that he fought with Stephen Hawking to show that there could be time machines in the quantum universe. So, and that's another, actually, it turns out that that's another thing, that another assumption in singularity theorem, that if you have time machines, in fact, that those are violated.
Okay, the last topic.
You mentioned, so all of these can be violated. I'm not saying all of them can be violated at the same time, but basically the main thing is that, I mean, the most important thing is that classical general relativity, we know because it doesn't have quantum mechanics in it, this will be violated. So this is really why singularity theorems, none of their originators, Stephen Hawking, God bless his soul, or Roger Penrose, neither of them actually believe in this. Right?
So this one's going to be called Were We Born Inside a Black Hole? One of the most intriguing and wild ideas in your book is that our universe itself might have formed inside of a black hole. Can you take us through that? What does it mean if it's true?
Yeah, so these black holes are things that were originally very speculative, but now we have evidence the black holes exist all everywhere. So we see lots of black holes that are eating stuff and emit X-rays. We even measured black holes merging together. We measured their gravitational waves, and their black holes we imaged at the center of a galaxy. So there are black holes in the universe. There are many of them. But what's inside the black hole is a big mystery. And if you kind of fall into it at some point, kind of you get denser and denser and hotter. Stars, we think, big stars, when they die, they could collapse into a black hole. So basically, the core of a star, for example, if it's heavy enough, it burns all these elements, fuses more and more elements until it makes iron. And iron, it turns out that you fuse it, you actually lose energy, you don't gain energy. So it's just when you get to that point, the whole thing kind of collapses into something hotter and denser. And at some point there, the density, according to general relativity, becomes infinitely big. Basically, there is nothing that really can stop the collapse of this massive core of a star. What happens beyond that is a question we don't really have an answer to. But one thing you may think, you may imagine, is that this is kind of like the Big Bang, but in reverse. Because the Big Bang, you had a very hot, dense universe that expanded and made that universe that we see today. But then the collapse of a massive star is some part of the universe that is getting denser and hotter. And it could be that when you actually, a star collapses and form this, what's known as a singularity, which is a very hot, dense phase, or something like, before it reaches there, it kind of bounces and makes another universe. So in that sense, then our universe, our Big Bang, might have been born inside a black hole. So we have billions of galaxies in the universe, billions of black holes in our galaxy. Maybe each of them contains a universe of its own with its own black holes. So this is kind of weird, but yeah.
What came before time? Let's go there, Niayesh. What do you think came before the Big Bang, quote unquote? And do you think we scientists can ever access that through experimental observational techniques?
That's an excellent question. Of course, we'd love to. And I don't think, I think our mission as scientists, especially as cosmologists, to reach back as far as possible. So I think we should try, we should do our best, but whether it's going to happen within my lifetime or not, that's another question. I think we could reach back. How far back we could reach, of course, depends on your technology and, of course, really your goal. But I mean, there are things that can let us see very far back. So universe becomes very dense and opaque at early times. So light has a hard time getting to us. But there are things that can get out. There are neutrinos. These are these weakly interacting particles. We can actually stare at the center of the sun using neutrinos. Maybe we could detect these neutrinos coming out of the Big Bang. Our technology is not quite there yet, but who knows? Maybe with advances in technology, we could see neutrinos coming out. There are gravitational waves that are even more weakly interacting. They could penetrate matter even more deeply. So they could come out of the very early phases at the Big Bang, or even before whatever was happening before that. Remember, I don't want to say that before the Big Bang, because we don't really know what was there. So it could have been anything. And Yeah, there could be other things. Sound waves, I think, is another thing I forgot to mention. That's another way you can actually probe inside the sun, because the sound waves can travel through the mantle of the sun or through the layers of the sun, and we do detect these sound waves coming out of the Big Bang. In fact, our best probe of the Big Bang right now, the sound waves that are emitted at the Big Bang, we see it in the cosmic microwave background anisotropy. So we do have these probes. The question really is how far back can we push them? And I think we hope to be able to do it with better technology, like the kind of experiments that you're working on, hopefully in the near future.
You argue that Einstein's biggest mistake wasn't the cosmological constant. So what was it really, and how is it still affecting us today?
I think we need a bit more context for that.
I think you say in the book that he couldn't accept the fact that the universe changes, that it was dynamic, and that bias still lingers, as you say in the book.
Yeah. Okay. So I think I'm kind of So I'm blanking out at that the bias that universe is static. You mean that bias? The universe is static? Okay.
Yeah, I mean, that was based on the evidence that he had at the time, but he was
Right.
kind of, resistant, reluctant to change his opinions about many things until and unless presented with evidence, which he never accepted in the case of EPR, for example. Right?
Right.
So anything you want to say? Let me rephrase it like this. Well,
Okay.
what do you think was Einstein's biggest blunder? Okay, and then we'll start again. Okay.
Okay.
Okay. So Einstein called the cosmological constant allegedly his biggest blunder. And then 70 years later, cosmologists looking at type 1a supernova found that maybe that wasn't a blunder at all. Now we see perhaps it's changing. So what do you think? What is the biggest blunder in cosmology, or the biggest blunder that Einstein really made himself?
I guess the biggest is kind of very subjective, I suppose. I think in terms of what Einstein's biggest mistake would have been was he kind of dismissed quantum mechanics, and that's one thing that, of course, is at the heart of our technology. The reason you and I can talk is that because we are employing the rules of quantum mechanics. But I think that in some sense that's also biggest the enemy of his theory of general relativity. So there are really this fundamental conflict between quantum mechanics and general relativity, and it's very surprisingly, in fact, Einstein developed both of them around the same time. Of course, he was not the only one who developed quantum mechanics, but like within a span of a few months, Einstein wrote seminal papers on quantum properties of light as well as general relativity. And it turns out that was really the battle that started started quantum gravity, even though he didn't really realize it. And we're still fighting that battle. But I mean, I think that the key to this is that we always make assumptions about what we think is the way universe should work, and these assumptions, some of them we do recognize them, and others we don't. And I think Einstein was impacted by that. He assumed universe was static, basically, at some point, and that those assumptions are still there. Sometimes we think theories should obey certain things, but we don't really know. We're not sitting in God's mind to say that, okay, God has to do things one way or another. So we have to admit that what assumptions could be wrong.
Absolutely. Well, Niayesh, this has been great. I hope that you have a wonderful rest of your weekend, and thank you for staying with us. It's a little later there in northeastern Canada, or southeastern Canada, I guess it is. For us,
Yes.
far north for us. I really enjoyed this. It's been too long, my friend. We should catch up more often, not only when you write a book, but congratulations on the spectacular accomplishment. You and Phil are to be commended. Even if I have my little spat with Phil, I still have a tremendous amount of respect for what he does. And this great book that he, kind of seems to have played a very large role in with you. So, Niayesh, thank you so much, and I can't wait to see what you come up with next.
Thanks a lot, Brian. This was absolutely fantastic. It was overdue for us to catch up. Hopefully, we can catch up more often.
Yeah, I'd love to do that. Do it in person, maybe too. Got to get you down here to San Diego, maybe in January. I know it's hard for you to leave Canada in January, but maybe we'll get you down here in the winter. Okay.
we need those snows. Then we need, otherwise, yeah. But something is missing from our lives. Yeah.
All right, my friend. Merci, merci. Thank you.
Hey everybody, I'm usually the one that asks my guests to judge their books by their covers, but today I'm asking myself to judge my own book by its cover. My newest book, Focus Like a Nobel Prize Winner, is chock full of advice, life tips, and focus and productivity tips from 9 of the world's greatest minds, Nobel laureates ranging from economics to peace to physics, of course. It launches September 9th, which is also my birthday. I hope you'll check it out. And my publisher's gotten Amazon to run a special just for listeners of the Into the Impossible podcast. You can get the Kindle edition for only 99 cents. That's less than a new pocket protector. So go to Amazon and get the Kindle copy today, because this special only lasts for the first week after launch.
Niayesh is incredible, and I think you'll want to pair this episode with my conversation with Thomas Hertog. We talked about all the theories that Stephen Hawking was promoting up until his very dying breath. Click here to watch that video. And don't forget to like, comment, and subscribe. See you next time on Into the Impossible.